All right.
Welcome to Reasoning.
I'm just going to watch some videos about reasoning and learn. I want to learn about reasoning models. This is like a two hour course, hour and a half course, maybe longer because I'm going to be doing stuff myself. But I want to understand some reasoning models and learn some better ways to prompt them. See if there's something better than what I do normally. So that's all I'm doing.
With O1, built in partnership with OpenAI. Your instructor for this course is Colin Jarvis, who's head of AI solutions at OpenAI. Colin, great to meet you.
Thanks, Andrew. I'm really excited to be working with you on this course.
In this short course, you learn how to best prompt and use OpenAI's O1 model. This recently released model has shown remarkable improvements in reasoning and planning tasks. In our very first short course, Isa Fulford from OpenAI taught some prompting techniques to give the best performance from GPT 3.5. She described chain of thought, which is a technique that gives the model time to think. With chain of thought prompting, you might instruct the model to think step by step and maybe also give some examples of step by step reasoning. And in response to that, rather than just providing the answer directly to a query, the model will process the query step by step. Here's an example from the 2022 paper Chain of Thought Prompting Elicits Reasoning in Large Language Models by Jason Wei and others from the Google Brain team. In this example, when using chain of thought prompting, you also provide the model with an example of a response that takes a problem and breaks it down into simpler steps. When responding to the query, the model creates a chain of simple steps which allows it to answer the question successfully. OpenAI has taken this to a new level and fine tuned the model using reinforcement learning to autonomously incorporate chain of thought, step by step reasoning into its response process.
While the performance we see today is impressive, what will be significant long term is test time or inference time scaling. We have found that the performance of O1 consistently improves with more reinforcement learning, called train time compute, and with more time spent thinking, which we call test time or inference time compute. This is a whole new dimension you can use to scale LLM performance. The O1 model, however, is not the right model for all situations. In the course, you'll learn to recognize what task O1 is suited for and when you might want to use a smaller or faster model, or combine those two. Here's the outline. We'll start with an overview of the O1 models and when you might want to use them, as well as how scaling performance at inference time works. Then you'll learn about prompting the O1 models to get the best performance. The best way to prompt O1 is pretty different from earlier models. You'll then learn how to use O1 to solve complex multi-step tasks with planning. In this case, optimizing a supply chain logistical challenge using an O1 orchestrator with a 4.0 worker. You'll use combinations of models together. O1 for planning a sequence of tasks, and faster, less expensive models for task execution. After that, you'll use O1 to do some coding. It's really good at this. Then you'll try out a really cool new feature, reasoning with images. Image understanding has traditionally been difficult to get into production, but with O1, we are seeing new levels of performance with these tasks. Finally, we'll wrap using O1 to generate and optimize your prompts, a technique we call metaprompting.
Many people have worked to create this course. I'd like to thank from OpenAI, Roy Ziff, James Hills, and Boris Powell. From deeplearning.ai, Jeff Lodwick and Ashma Gagari had also contributed to this course. All right, let's go on to the next video where you learn more about the details of how O1 was trained.
All right. I'm also curious because this is kind of an old course. I wonder if there are other reasoning model things. Let's see from deep learning. Maybe, maybe not. Because we are now in the '03 and '04 era. In any case.
This lesson will be a general introduction to O1 to get you familiar with how it's so different, how it functions, and what people are using it for. Before O1, you could think of most models as like children. They always say the first thing that comes to mind. As they grow up, they need to be taught a valuable lesson, that they should think before they speak. What makes O1 so different is that it explicitly thinks before it speaks every time. This helps it reach new levels of performance at complex tasks in domains like math, coding, science, strategy, and logistics. The way it does it is by using chain of thought to explore all possible paths and to verify its answers as it produces them. This means that O1 requires less context and prompting in order to produce very effective results. We've released our first two models in the OpenAI O1 series. The first is O1, our mainline reasoning model for complex tasks that require broad general knowledge, which includes function calling and image input. We also have a faster, more cost-efficient version called O1 Mini, which is tailored for coding, math, and science, and designed for those more cost or latency sensitive use cases. The thing that makes the O1 family of models so different is how they natively integrate chain of thought into how they solve problems. Let's take an example where we give these scrambled letters and we translate them for the model, and then we give it a new problem to solve. The way it solves it is something like this, where it thinks through what it's given and talks itself through how to solve the problem. It recognizes the example and then understands the transformation that took place here. Then it comes up with hypotheses and tests them. For example, it thinks maybe there's an anagram or cipher here. Then it notices that the ciphertext words are exactly twice as long, so maybe then it comes up with an idea to test. It tests it and finds that it doesn't work, but uses that to iterate to a new hypothesis, which gets it to the right place. And this, in a nutshell, is what makes O1 so special. Rather than you having to prompt it to do this, we've trained the model to natively apply this reasoning process so that it can work through more complex problems in many disparate domains like science, law, coding, and math. This introduces a trade-off when you're using the O1 family of models, where you generate extra completion tokens, which you don't actually see, but which the model is using to problem solve your task. Let's look at how it works. We can see here that completion tokens can be broken into two distinct categories. We can see our gray reasoning tokens here, and the actual output tokens, which are the tokens which you are provided for your generation. It's important to note that reasoning tokens are not passed from one turn to the next. If you want to do something like this, you'll need to prompt the model to output some kind of reasoning which you can choose to pass from one turn to the next. What this means is you also need to consider those reasoning tokens in the cost of what you're paying for, and also when you're calculating your context limit, because those reasoning tokens do count towards the context limit, and if your output goes over and above that, the output will be truncated. Two of the key breakthroughs that led to O1's increase in performance were, first of all, recognizing that during the post-training process, the more reinforcement learning we did, the more accurate the model got. But
That's actually fairly interesting, I believe.
what was possibly more surprising was the more we allowed it to think at inference time, we got an even sharper increase in performance. So the key breakthrough here was the ability to think for a longer time at inference time and get better results. The other key breakthrough that led to the increase in performance with O1 was teaching it to verify outputs via consensus voting. The way this works is that we generate a bunch of solutions and train the LLM to choose the most common one. You can think of this as similar to when we sample at low temperature. In one paper, we saw a math benchmark go from 33% to 50% improvement purely due to consensus voting. Consensus also flatlines before 100 samples, so you don't need a huge amount of samples to realize the performance improvement here. So what's the significance of all these breakthroughs? The results of O1 have so far been really good. For example, here's one benchmark that shows the difference between GPT-4o at 13% on this benchmark and the new O1 model, which got up to 83%, a huge improvement. Similarly at code, where GPT-4o scores 11%, and we see O1 at 89%. And science, where we don't see as big of an improvement, but still 20 odd percentage point improvement on this benchmark. This carries on to other families of benchmarks. For example, math, where we see a giant 30% improvement from O1 over 4.0. Science, 20 to 30 odd percent improvements. A variety of different exams, most impressive one here being the LSAT at almost 30% improvement. And lastly, the MMLU categories, where there was improvement across the board, with the highest scoring being a 98.1% on college mathematics, which is super impressive and a massive improvement over the previous family of GPT-4o models. So how does the O1 model actually work? The key factor is that it uses large-scale reinforcement learning to generate a chain of thought before answering. This chain of thought it produces is longer and higher quality than what you can typically attain via prompting alone. It also contains behavior like error correction or trying multiple strategies and selecting the best one, or naturally breaking down problems into smaller steps. There's a bunch of examples of these chain of thoughts on the research blog post if you want to dig a little bit further. One other area that O1 represents a new standard of performance over the 4.0 models is abstract reasoning. I'll give you one challenge here. We gave GPT-4o 16 words, and it was challenged to identify the 4 categories which united those words, and then place the right terms in each category. And you can see here that its performance was fairly haphazard. So other than approval, it was only able to identify one other category, which was movement/action, and it misidentified one of the terms. Whereas when we tried it with O1, it was able to correctly identify both the 4 categories and all 16 of the words. The reason we're so excited about this kind of abstract reasoning is it doesn't easily fit into the same bucket as coding, math, or any of the other benchmarks that we've shown, but it shows some of the other emergent capabilities that the O1 model is starting to show. And we're very excited to see you all test it with your own use cases to figure out where else these kind of abstract problem-solving capabilities are going to be significant. The last area we want to highlight where we've seen significant emergent capability from the O1 family of models is where we have a generator verifier gap. What we mean by that is, for some problems, verifying a good solution is easier than generating the perfect solution up front. For example, with Sudoku, with math, with programming, you can often generate a half-decent solution, verify it, identify the issues, and then use that to iterate to the next one much more easily than building the perfect solution up front. There are also examples where this verification generation approach doesn't work. For example, for information retrieval, where the question does need to be answered correctly the first time, or with image recognition, where you need to correctly identify what's in the image first time. But where a generator verifier gap exists, and we have a good verifier that can run the verification process, we can continue spending more compute at inference time to achieve better performance. And for these, we're seeing O1 demonstrate great capabilities. So where might the O1 models actually be used? In areas like data analysis, interpreting complex data sets like genome sequences, or mathematical problem solving. We've seen a ton of benchmarks here, but this is an area where we really see a step change in performance versus the previous family of models. Similarly, experimental design, so coming up with innovative approaches for niche domains like chemistry or physics, is another area we've seen pretty encouraging results. Scientific coding as well. You'll notice a common theme here, a lot of STEM subjects, a lot of math, a lot of coding that we're seeing great use cases for O1. Biological, chemical reasoning is another one, and algorithm development. Literature synthesis is the last one that I want to highlight here, where reasoning across multiple research papers to form coherent conclusions or summaries is another area where we're seeing great capabilities from O1. So let's recap the key takeaways from this introduction to O1. The first is that the O1 family of models scales compute at inference time by producing tokens to reason through the problem iteratively. O1 gives you more intelligence as a trade-off against higher latency and cost. So it's not appropriate for all use cases. It can also perform really well at tasks that require a test and learn approach where it can iteratively verify its results. Some of the great emerging use cases we're seeing are planning, coding, or domain-specific reasoning in fields like law or STEM subjects. So let's jump into some of the practical applications that we're seeing and walk you through how you can make use of O1 for your use cases. I'm going to show you a quick example of how O1 works within chat completion. First, I'll import my API key and set up my OpenAI client. I'm going to set O1 mini to be the O1 model that I'm going to use. And I'll queue up a chat completion request. You can see O1 requests are exactly the same as your typical chat completion request. We specify an O1 model, and I'm going to give it the classic question, how many R's are in strawberry? We'll generate this, see what comes back. Let's have a look at the response object. We can see here the standard chat completion response. We've got a chat completion message in here. We have the output. The word strawberry contains 3 letters and a couple of other outputs. Now, the thing I want to focus on here is what makes O1 different. Here you can print out the tokens. We're going to focus on the prompt tokens, the total completion tokens, and then the constituent parts of the completion tokens, which consists of the reasoning tokens and the output tokens. If we print these out,
1,500.
you'll see that
1,000,
the model
1,000.
did a ton of thinking here. So we gave it only 15 prompt tokens, but it produced over 1,000 reasoning tokens to reach the output. And this highlights the key trade-off with O1. You're getting much greater intelligence, but in this case, we paid a 10x premium in terms of the amount of output tokens that we paid for to get this. This is a key thing to consider. You don't use O1 for everything. It's only for those use cases where the increase in intelligence you get is worth the trade-off in latency and cost. Look forward to seeing you on the next lesson where we dive into how to prompt O1 to get the best performance out of it. This lesson will be a general introduction to. This lesson will cover 4 key principles we've worked out during the first months of using O1 models. These aren't exhaustive, but they should give a great starting point for you to explore the differences between our other models and this new family of reasoning models. We're interested in hearing what principles work best for you. All right, let's take a look. There are 4 principles for prompting the O1 models. The first is to be simple and direct. Try to write prompts which are straightforward and concise. You'll find that direct instructions yield the best results with these models. The second is that no explicit chain of thought is required, and this may be somewhat different from what you're used to with LLMs. You can fully skip the chain of thought reasoning prompts that you used to provide, like think step by step and things like this. The O1 models are trained to infer and execute these itself without providing your own breakdown. The third is to use structure. So try and break complex prompts into sections using delimiters like Markdown or XML tags. The structured format will enhance model accuracy and also simplifies your own troubleshooting. We'll see a couple examples of that here. And the fourth is to show rather than tell. This comes back to our first principle. Rather than giving a lot of prompt to tell the model how to act, it's often better to give it 1 or 2 contextual examples to give it understanding of the domain of your task. Let's jump across to the code and see how these work in practice.
Arrow's in the wrong direction there. I guess it is in terms of forward in the movie, forward in the video, but code's over here. Okay.
You'll start off by importing your OpenAI API key and the variables that you'll need to run these. You'll notice here that we've initiated the OpenAI client with our API key, and we've also imported a GPT model and an O1 model. For the purposes of these lectures, we've used the GPT-4o mini model as our kind of base model to compare against. And for the O1 model, we've used O1 MIDI. Both of these are for reasons of cost and latency. These are faster, cheaper models. We'll start with the first two principles, which are being simple and direct, and that no explicit chain of thought is required. I'll start with an example which breaks these rules. Looking at this prompt that I've pasted in here, we're instructing the model to generate a function that outputs the SMILES IDs for the molecules involved in insulin. Then we moved on to give it some chain of thought instruction. So we've asked it to think step by step, and we've given it 3 steps to work through. And we've also given it a starting prompt to kind of give it a hint as to how we want it to start. Now, with O1 models, we've trained it to act and reason in the way that we think is optimal to solve these sorts of problems. So we're going to see in a second why it's better to just give a simple prompt without these. But let's run this first to see how the model behaves with this explicit chain of thought prompting. We're going to display the results here. You'll notice I've given a couple of HTML headers because the model's outputs can be pretty verbose. So we've tried to signpost where the content starts and ends. Having a look at this, we can see the model's output. So the first thing is that it has followed our instructions, but
Okay, so we get the model output messages. Okay. And here we convert it. Oh, gotcha. I see. I see. Why markdown output beginning? I guess he's wanting to structure it like almost like XML.
it's followed them explicitly. So it's given us a large number of preceding steps before actually going and solving our problem. This is one of the consequences of adding explicit chain of thought. The model will...
Gotcha. Okay, so I say think step by step. It gives me step by step before giving the actual answer. What if I were to delete all that? Generate a function. It generates the function. It just does it quickly. Okay. I see. I see. Identify all the molecules. Okay, I see the issue.
will often explain itself a couple of different times, and you may end up with an overly verbose output. We can see here that it finally creates the function in step 3. Again, it's reprinting the SMILES codes, the amino acids that it's going to process for this task, and then it gives us a sample output. Then at the end, it summarizes the explanation and reasoning that it used to come to this and gives us a conclusion. So it did answer our question, but it gave us a lot of extra information, which is probably not needed for getting the output that we're looking for. So let's change the prompt, apply our principles, and see how the output differs. This next prompt applies our 2 principles. You'll see here that it's simple and direct, telling the model to generate a function that outputs the SMILES IDs for all the molecules involved in insulin, and contains no explicit chain of thought prompting. You'll run this and get some results. Here we have the same formatting that we had above. And here you'll see a quick description of the task. It describes what insulin is, how it's going to get the SMILES codes, and then jumps directly into the code. So a much more efficient response this time. We've got our full Python function here, which we can run, and an example of it being used. It then provides a little bit of explanation at the end as to the assumptions it was made, and a sample output of what it thinks is going to come out the other end. It also supplied an alternative approach, and finally, a conclusion. So the point here is it didn't require that explicit chain of thought prompting. We've trained the model to provide what we think is an effective level of explanation with its responses, and that is always a good place to start. That is not to say that you won't need to add your own chain of thought prompting for specific or very nuanced tasks, but it's always best to start from a baseline of being simple and direct with no explicit chain of thought prompting. Let's move on to the next principle. Feel free to pause here and do your own analysis using these principles. You might want to look for the molecules involved in ibuprofen or aspirin or other common compounds. The key thing is to try breaking those rules, so giving it a verbose prompt or providing chain of thought prompting, and then looking at the impact it has when you simplify and trust the model to do its own chain of thought prompting. The next principle is to use structure when prompting O1. In this case, I've got a lengthy prompt here where I'm prompting the model to act as a customer service assistant.
It's not running. What's happening? Oh, there it is. Okay. Took much longer than I expected. I thought the old one mini models were faster. Oops.
You'll see here that I've used XML to
Oops.
the impact it has when you simplify and trust the model to do its own chain of thought prompting. The next principle is to use structure when prompting O1. In this case, I've got a lengthy prompt here where I'm prompting the model to act as a customer service assistant. You'll see here that I've used XML tags to give structure to the prompt. So at the top, we have a set of instructions. And in those instructions, we've told it to follow your policy. We've then used structured formatting to provide it a policy tag so that it's very clear to the model what we're referring to when we say
You're a customer service assistant for Anticorp, provider of fine storage solutions. Your role is to follow your policy, which is down here. This is the policy. I don't see where the policy ends. Oh, here. Your role is to follow your policy to answer the user's question. Be kind and respectful at all times. Instruction, policy. Okay. I personally don't use XML often. I usually use Markdown with code blocks, so I'm going to switch over to using XML. Well, let's get the justification
the
first.
policy. And then within this policy, we have a series of different criteria. So what it's allowed to do, how it handles refunds, and compliance. So which policies it should adhere to. We're then providing a user input at the bottom where we have a user query tag. And within that, we have what the user is explicitly asking for. I'm going to run that and print the prompt so that we can see it in full. There we are, our instructions, a policy, and then we will add the user input on the bottom. Here we have our request. So we're using the O1 model, and the content is going to be the structured prompt with the user input appended on the bottom. Let's run that and see what the result is. We'll print the results to see how the model's responded. It looks like it successfully followed the process. So we said that a product didn't meet our expectations, and it matched that to the return process successfully. Let's give it one more test to see whether it maintains performance if we ask it about one of the other policy areas. Here's another user query. You can see here we've asked it to write me a haiku. So in this case, we're breaking the policy. We're asking for something that the model shouldn't comment on.
Okay, so policy, refunds, you're authorized to give refunds, ensure recording complaints, listen attentively to the complaints, provide assurance, provide product information, simply supply accurate and helpful information, professional conduct, maintain a polite and respectful, blah, 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 compliance, adhere to all corp, protect customer privacy, okay. If you receive questions about topic outside of these, refuse to answer them and remind them of the topics you can talk about. Gotcha. That seems very important. So we're asking for a haiku, which should tell us no. Sorry, but I can't help.
If you run this, you'll see how the model responds. Here's the same request as before. This time, we'll take our structured prompt, add our refusal question, or the question we're expecting to be refused, and let's see what the output is. Great. It's adhered to its policy again. In this case,
So there are ways to break it. Here, I just wanted to write more words, so I wrote policy. That didn't really work. I wrote refund, and that refunds are a part of the policy, of course. So kind of overwrote, or subverted the policy a bit because I could get a haiku. Reasoning shines bright, refunds processed with great care, trust in any corp.
refusing this question because this violates its policy rules. So we've seen how providing a structured input prompt to O1 models can ensure that they'll follow the instructions with greater accuracy. We've combined that with being simple and direct, and we haven't given any explicit chain of thought prompting, so we're starting to build up some good principles. I'll move on to the final principle. The fourth and final principle is to show rather than tell. You'll see here a prompt where we're asking the model to pretend to be a lawyer specializing in competition law. So again, we've given a
So also, it didn't give us this video didn't give us the negative thing, which is that oh, I didn't remove all the tags. It looks like it still works even without the XML. Let's try again. It kind of works without XML. It looks like it is breaking a little bit more when I remove the XML for the user input. Hmm. It's gonna re-roll it. I think the models are Set to be deterministic. Yeah, they are. Okay. So it's just a little bit less reliable without the XML tags. I guess it makes it slightly easier to read with XML, but maybe not crucial.
A prompt structure at the top, and a policy is, again, telling it to maintain clear and accurate information about competition law and also to avoid giving specific legal advice without sufficient context. There's a simulated user query here. So a customer asking that a larger company is offering suppliers incentives not to do business with them and asking if this is legal. Going back to the principle here, at this stage, we have not shown rather than told. We've just given it instructions and we haven't specified how we want it to act. If we run this, we'll see how it performs out of the box. I've got another request here, our base prompt with the query appended to the bottom. Here we'll examine the results. You can see the model has acknowledged the question of the user and then provided a write-up. Great.
Another question I have. So here we're not explicitly telling it to use Markdown anywhere. Is it just natively always using Markdown?
Great. But in the case of legal answers, I actually want the model to use specific references to evidence the position that it's taken. I could tell it to do this explicitly by adding more prompt, but instead, I'm going to provide it an example input and output along with my prompt and trust that the model will learn from the style of what I've shown it. Again, I don't have to explicitly tell it. I'm going to show it by giving it an input-output example as well as the prompt. Here's our updated prompt, which adheres to the principle of showing rather than telling. You'll see the same two structured elements. We've got a prompt and a policy, but after those, I've included an example tag. And within that, I've got an example question and an example response. If I scroll across here, you'll see that I gave specific examples. And then I also referenced the relevant acts which cover the legal recommendations that I've given.
I wonder why he wrote, like he's writing this with the breaks, but then the examples are not written with I guess they're just not important, but odd to me.
You can see that I've done this in each one of the points that the model has supplied. What I'm hoping by doing this is that the model will learn that I want a series of bulleted reasons for my question, and wherever possible, that I want it to reference itself. So let's run another example question and see how the model responds and see whether it manages to reliably follow what it's seen here. You're going to run this new prompt with the example included with the same legal query as we had the first time. We'll now submit our updated prompt.
So we got the key considerations, which is here with various examples or various points. And then we've got the recommendation there with bullet points. It's the bullet point. Whereas in the above, we just had a general overview. We do not have recommendations. We don't have key considerations. And do we have, he said he wants a specific thing. Oh, we got section 2 of the Sherman Act. Okay, we've got specific. Gotcha.
Prompt
It did work.
with the same query from the first question. Time to display the results. You can see here again a preamble and then our bulleted reasons. And great, it looks like it's successfully learned that it should reference itself. So We can see an example here. We can also see an example here and an example here. Now, it's given me a couple of examples, but it hasn't referenced every one of these bullet points. So this is telling me I might want to give it maybe 2 or 3 examples so that it can learn even further by showing. You can always add prompt, but as a general principle, it is better with O1 to give it the examples and let it figure out the reasoning that it needs to do to get consistent performance. But as a general principle, it is better with O1 to give it the examples and let it figure out the reasoning that it needs to do to get consistent performance. One of the great use cases where O1 models shine is creating a plan to solve a task, given a set of tools to carry out the plan and constraints to set bounds around the task. This kind of use case would be very slow if we used O1 for every step. So what we'll do is generate a plan with O1 Mini and then execute each step with GPT-4o Mini. This trade-off of intelligence against latency and cost is a practical one that we've seen developers use to great effect so far. All right, let's go. Let me tell you about the overall architecture of the task so that we don't get lost in the details as we go through the code. You'll begin with a scenario. This comes from a customer where they're making an ask which requires multi-step logic to answer that scenario. That scenario will be given to O1 Mini, who will have at its disposal some instructions of how to build a plan, and then a number of tools which it can use to carry out the plan. This is a great use case for O1, where we use its multi-step reasoning logic to build a durable plan before we then engage 4o Mini as a worker to carry out each step of the plan. Once the plan is completed, we'll have an answer, which we provide back to our customer. Now let's nip into the code and see how this works in practice. You'll start by importing your OpenAI key and initiating the OpenAI client and the O1 and GPT models. You'll first define the constraints that this scenario will be bound by. Your first variable is a message list. Because our 4o worker is going to loop through multiple steps, we need a list of messages to accumulate the history so that the worker can tell what steps it's performed of the plan that we've come up with. Then you've got a bunch of context. I'm not going to go through every variable here, but essentially we have an inventory, a order that a customer wants to place, and then we have suppliers, which we can use to supply us with additional material if the customer asks for something that we don't currently have. We then have a few other variables like the shipping options and the metadata of the customer who's going to be giving us our scenario. The last element is the state. So because we're going to go through multiple turns of conversation, we will maintain conversation state. And when you take this and apply your own scenario, you can consider whether you want to wrap this in an application where you clear down the state at certain points to allow the customer to submit multiple scenarios.
What is copy.deepcopy?
Copy.deepcopy is a function in Python's copy module that creates a new compound object and then recursively inserts copies of the objects found in the original. This means that it duplicates not just the top-level object, but all of the objects it references, ensuring that changes to the copied object do not affect the original object and vice versa. This is particularly useful for complex objects like nested lists or dictionaries.
Okay, so that's just copying all this, and this context this is a library, I believe it's called, but these are all different variables, I think. I don't know a lot about Python or coding in general, but this is like a variable which has a variable. I don't know. I don't know. Maybe that's a variable. There's a different name for this because it has, I don't know. And then it's within a list, and the list is within another list or a library. I don't know. So, but this thing, this object, is context. So that's being copied into what is called initial context, but it's being copied in a specific way such that all of these things are also copied independently as separate new things, such that when the context changes, the initial context doesn't change. So if I change, all right, well that's enough detail, I think. I think I understand.
Next, you need to define the prompt, which dictates how O1 is going to go about building a plan to solve the customer's scenario. This prompt consists of a few main sections. The first is where we define who it is and what its task is. So we're telling it that it's a supply chain assistant, and its task is to review the challenge that it's been set or the scenario and create a detailed plan to answer it. We tell it that it will have access to an LLM agent, and then we give it a list of functions. Now, it's important to note here that the O1 model isn't going to be provided with the OpenAI function calls. Those will be given to the worker, the 4.0 mini model, which will be doing the work for it. But O1 needs to know what those functions are and what they roughly do so that it can build up that multi-step plan for the 4.0 mini worker to carry out. So, for example, it needs to know that there's a fetch new orders function, which will allow the 4.0 mini model to check the status of new orders that have come in and decide whether to fulfill them or not. Underneath this, we've given O1 a set of instructions which tell it how to lay out this plan so that we can then parse it and provide it to 4.0 mini to carry out.
Okay, break your plan to step-by-step functions because 4.0, oh, so yeah, 4.0 needs step-by-step functions. Numbered subactions are lettered. New lines. Okay. If then else statements. Okay. Okay.
Next, we'll define the functions themselves. It's important to note that O1 can now do function calling, but we're not going to use it for this scenario because we want it to come up with that multi-step plan to give to 4.0 mini to execute. If we wanted O1 to carry out each step bit by bit, we could supply it OpenAI function calls. But in this case, it's going to create the plan for 4.0 mini to carry out. Now we'll define the GPT 4.0 system prompt. So the prompt that dictates how that 4.0 mini worker is going to do its job. Again, we've given it a personality. So you're a helpful assistant. We're telling it that it's responsible for executing the policy that it will be given, and its task is to follow the policy exactly as written. We also ask it to explain its decision-making process across various steps, and this will come in handy later. So as it goes through the plan, it will decide whether to update the customer on the progress and whether it's hit any blockers. We then give it step-by-step instruction. Again, referring back to the principles for prompting O1, we don't give O1 explicit chain of thought prompting, but given that we have a 4.0 mini worker here, it is useful to give it some chain of thought to help it make the right decisions. And lastly, we'll instantiate that policy that was generated by O1, which is that plan, and give it to 4.0 to then execute each step.
I was just looking for that. Where is policy created? So I guess the output of O1 will be what is called the policy, but we don't have that. Oh, we're defining the function. Okay. Right here. Define the functions. So we can call them. Functions. I'm just trying to see where policy is. Here it is. No. Plan, GPT policy. Replace policy with plan. There we go. Okay. So the output of O1 is going to be called plan. It's the output here of O1. Output of O1 is plan. That's going to be replaced by policy. Okay. I got to kind of, I want to understand a little bit of how the coding stuff works and the syntax of it all. Vaguely, but I'm getting it.
To allow 4.0 Mini to take action on each step of the plan, it needs to have OpenAI function calls. We've defined those here. You'll see a long list of function calls, and I'm not going to go through each one in detail, but just picking out one of them, this function allows us to check the production capacity. So it will look at the amount of components that we have and figure out how much capacity we have to create more units. And again, we've got our standard OpenAI function call parameters here. So in this case, a time frame, which is an enum that it can pick from. Each one of these functions will tie to a step of the plan, which O1 has produced for it, and will allow 4.0 Mini to take action. Those OpenAI function calls map to Python functions, which actually execute the results of each function call. Again, looking at the same one that we looked at a second ago with the OpenAI function calls, here's the Python function, which is implemented based on the results of that function call. So we pass in that time frame, and then we get back a JSON, which the 4.0 Mini model will assess and use to decide whether it moves on to the next step of the plan. Now that we've defined the input variables, the 4.0 and O1 system prompts, and the function calls with their Python definitions, we can move on to creating a function which will knit all of this together to orchestrate the process. The first step is to take in a scenario provided by the customer and call O1, who will produce a plan. We then take that plan and initiate a 4.0 Mini worker. That 4.0 Mini
Input scenario, that goes into O1. Output goes to plan. Plan, append message, type plan, content plan. So you get a I guess I don't know what append message is. So what is it appending? What is it appending? What is this function? Okay, hold on. Append message, generating plan. Okay, generating plan, it generates the plan. Status, message. I guess I'll just have to see what happens when that happens, because I don't understand that.
worker.
What is the append message function?
The append message function typically refers to adding a new message to a collection of messages, such as in a chat application or a logging system. In the context of conversational AI or chatbots, an append message function might add a new user or system message to a list of messages that represent the conversation history. This helps in maintaining context, allowing the system to generate more coherent and context-aware responses.
Will loop until it's carried out the whole plan, and then return the messages.
Loop? Where are we getting loops from? Append message, generating plan. That's just all text. Okay. Status, generating plan. Calls the plan. Then it says plan, and it gives us the plan. Then status, executing the plan. Starts to call O4 40, sorry, calls 40, giving it the plan. Then it gives a status, processing complete. So I guess this is the looping part. It just keeps doing the plan. That's a whole other thing, which is, oh, this is the message. Oh, okay. This is a pin message. I just thought it was a regular function. This is a defined function. Okay. Now it all makes sense. Gotcha. So we call 40. This is where it loops, as he said, looping. Gotcha. We got a for loop. That makes sense. Okay. We're all here. We're all making sense.
Initiate and definitions, we can move on to creating a function which will knit all of this together to orchestrate the process. The first step is to take in a scenario provided by the customer and call O1, who will produce a plan. We then take that plan and initiate a 40 mini worker. That 40 mini worker will loop until it's carried out the whole plan and then return the messages. And that is what we will provide back to the user to tell them how we managed to perform against the scenario that they gave.
Yes.
If you'd like to look into the underlying details behind that orchestration wrapper, the first function is the append message function, which takes in a message and decides which variables to include with it to give 40 mini context to continue carrying out the plan. The next function
get the message. Message get. Message type. Okay. Oh, message is this. Okay. You get the message. Message list. You get a list. Message. I guess this is not super important for me to know. I kind of vaguely understand it.
provides the scenario provided by your customer to O1 and generates the response. This plan is what we're going to provide to 40 mini to then carry out that scenario. The last orchestrating function calls GPT-4o with the plan generated by O1 and uses that to carry out the plan. You'll see here that we initiate a while loop, which begins producing tool calls with GPT-4o mini and decides what action to take based on the content of those tool calls. So it will keep looping until it receives an instructions complete function, at which point it will break. Now you defined all the variables you need. So the only thing remaining is to come up with a scenario that the customer wants us to carry out. In this case, we've said that we've received a major shipment of new orders. We're asking O1 to generate a plan that gets the list of awaiting orders and determines the best policy to fulfill them. We've given it some idea of what the plan should include, and we've also given it an overriding directive that it should notify the customer before completing. Lastly, we've given it a criteria, which is to prioritize getting any possible orders out that it can, while placing orders for any backlog items. With that, we're ready to start generating the plan. You can see the plan that O1's generated for you laid out nicely here in Markdown. The first step is to retrieve new orders.
I wonder why he says this is in Mark. I mean, it is in Markdown, but it's not rendered Markdown. Generate plan. That was very quick to generate the plan. We got the plan.
You can see here where O1 has specified the exact order with these openai function call that 40 mini should use to carry out this step. Next, it's asked it to process each order individually. And then within that, it's given extra detail. So for each order in the list, extract these variables, check availability, and handle any backlogged quantity. If there's backlogged quantity, we've given it if then else logic to
guess I think the plan should not be
Availability order individual.
should not be deterministic, right? Yeah. That's pretty cool. Fetch and review orders. It says retrieve new orders, right? Process. He says process. It's Canadian, I guess. Process each order individually. That's the same. Then we get check inventory availability number 1 for me. Number A1 for me. 2A1. But for him, it's 2A2. So it's not deterministic because the plan is being generated by O1.
Individually. And then within that, it's given extra detail. So for each order in the list, extract these variables, check availability, and handle any backlogged quantity. If there's backlog.
I wonder if in this case, would somebody want to make the plan and then just have the plan and use the plan as it is? Or would you always want to have O1 generate a slightly different plan every single time you run this? It seems a bit, well, I don't know. I don't know in what case you would want the plan to be slightly variable. And there's no checking the plan and making it better. So why bother with having a variable plan?
Quantity. We've
Just a
given it
curiosity.
if then else logic to go about actually handling that. Once it breaks out of that, it will arrange shipping for the available inventory and notify the customer. We give it a little bit of logic here to tell it what to do if the order is fully fulfilled, if it's partially fulfilled, or if there's a backlog that it needs to let the customer know about. Lastly, it will finalize the instructions and call instructions complete, which will break out of the while loop and provide the answer to the customer. Next, we'll go through the actual steps which 4.0 Mini carried out to check that it followed this plan as specified. The last thing to note is that O1 has adhered to the prompt engineering principles which we mentioned earlier by providing a structured prompt so that 4.0 Mini will find it easier to follow. As we go through the 4.0 Mini actions that took place, it's key to refer back to this and understand whether or not it actually properly followed these steps as specified. To review the actions that 4.0 Mini took in more detail, I'm going to print out the messages so that they're a little bit easier to read. I'm going to skip past the O1 policy because we've already gone through that and start with the different actions that 4.0 Mini took. So first we can see that it called the fetch new orders function, and that got us one new order, which is a quantity of 200 of product ID X200, which we can see here. We then see that it called the get inventory status function to check whether we actually have the inventory to serve what the customer asked for. And we can see that we do have that particular product, but we only have 50. So it's going to need to order a few more if it's going to be able to fulfill the customer's order. The next thing 4.0 Mini did was allocate the stock that it did have. So we can see here that it allocated the 50 units that it had. To fulfill the 150 units that it doesn't have, the first step is to get the product details and figure out what components are needed. We can see that this comp X200 component is what you need to build one of these units. It then checks the available suppliers, finds that we have 2, and then calls the first one to figure out what the available quantity is. It then places a purchase order for the quantity that it needs, which is 150. There's 500 available, so that's okay. The next step is to check whether we have production capacity to actually produce those once we have the raw materials. You can see that it checks for the immediate production capacity, and we only have capacity for 100. So it schedules a production run for 100 immediately. And then it goes back and checks the production capacity for next week and is able to schedule the remaining 50 units to be produced next week. The last step is to calculate the shipping options for the units which we have right now before finally sending an order update to the customer, telling them your order has been partially shipped, the remaining items are being processed and will be shipped shortly. and then successfully closing off the process. So, pretty impressive. We've been able to implement an agentic flow whereby O1 acts as the orchestrator, creating a plan and then handing to 4.0 Mini, who then executes the multi-step plan in sequence. Now is a great opportunity for you to take a step back and think about where you might have opportunities to use this kind of planning paradigm, using the intelligence of O1 and combining that with the low latency and cost of 4.0 to carry out these complex multi-step agentic processes.
Well, it's time for me to step back. I have no usage for this, I don't think. But where to use reasoning model? I'm just saying reasoning models because we have O4 now. I do often do this when I do some vibe coding. I create plans with O4 and then I execute those plans with Claude. But it still doesn't really make that much sense. Well, I don't know. I don't know because I've got to rethink a couple of things because I often use chain of thought instructions with the thinking models, and it seems like, well, we went through that exercise. It is not the right thing to do. We should not be doing chain of thought instruction with the thinking models. So there's something about that that needs to be figured out. But anyway, I often use O4 to create a plan for coding and then use Claude to actually execute the plan for coding. So this is where I use that type of thing. Where else could I use it? I don't know. And Claude is already a thinking model, so it doesn't really it's not super necessary.
Next, we'll change our focus from planning over to a very common use case for our O1 models, which is coding.
Okay.
Look forward to seeing you there. Building on the approach we use with planning, you're going to use O1 to help with a coding task. O1 performs best with simple, direct prompting to both create new applications and to edit existing ones. To test this, you'll run 2 coding competitions between O1 Mini and GPT-4o to create a net new application and to edit some existing code. Let's get coding. In this lab, we're going to...
And to edit. So O1's good at editing code. Well, I'm sure we'll learn. Reasoning models are good at
learn how to
editing.
use O1 to assist us with creating an original app using code and then editing existing ones. In this lab, we're going to learn how to use O1 to assist us with creating an original app using code and then editing existing code using O1. To start with, we'll import our variables, so our OpenAI API key, and again, the GPT model and O1 model that we've been using so far. We'll begin by creating a React app. To start with, I'm going to define a function which will allow us to get a chat completion response. The next thing you'll do is define a prompt for how O1 and 4.0 should think about creating this app. So pasting in a prompt here where we give instructions to create an elegant, delightful React component for an interview feedback form. We give it some criteria for how this app should perform and what the overall goal is.
So creating an app, I don't know what a React app is, if that's a specific type of thing. What is a React app?
A React app is a web application built using React, a popular JavaScript library for building user interfaces. React allows developers to create reusable UI components and manage the state of an application efficiently. With React, the user interface updates dynamically as the underlying data changes, making it ideal for developing interactive and responsive web applications. React apps can be rendered on the client side, on the server side, or even be turned into mobile apps using frameworks like React Native.
And could that this is just a UI, it's just a front end UI, and that could be used for any other. It can be used for any back end application.
Exactly. A React app is primarily focused on the front end, which means it handles the user interface and user interactions. It can communicate with any back-end application or API, regardless of the technology stack used on the server side. This separation of concerns allows developers to build a robust and dynamic front end that can interact with various back-end services.
Gotcha. Gotcha. All right.
And a couple of reminders here. I've included these because I'm working with 4.0. Generally, I wouldn't for 0.1. So now we'll generate.
He's including the make sure to call element form feed form. He's saying this part, start code with use client. Respond with the code only and nothing else. He's only saying that because it's 4.0.
Overall goal is, and a couple of reminders here. I've included these because I'm working with 4.0. Generally, I wouldn't. Criteria for how this app should perform and what the overall goal is, and a couple of reminders here. I've included these because I'm working with 4.0. Generally, I wouldn't for 0.1.
Gotcha.
So now we'll generate code using both 4.0 and 0.1, and then we're going to render both apps and visually compare the quality of each. You'll begin with 4.0 here. We'll get it to generate the app, we'll render the app, and then we'll do 0.1, and hopefully we'll see a marked improvement with the 0.1 model.
Hopefully.
Let's kick off the generation. Now that the code's done, let's print it and have a look. There we are. I'm just going to copy this out, render it in our app, and we'll be ready to inspect the results. I'm going to display a static image of what I've gotten when I loaded that code into the app.
Oh, I don't have this. What is the React? Okay. It's not really hands-on if I'm not really getting the. Where can I upload JSX? Is that what that's called? Where can I upload this to see a React code actually rendered?
To see your React code rendered, you can upload your JSX files to various platforms that support front-end hosting or provide an online code sandbox. Here are a few popular options. 1. Code Sandbox, a powerful online editor that lets you create, share, and deploy React projects easily. It has built-in support for React and shows the rendered output in real time. CodePen, another online editor where you can create small React projects called pens and see the output right away. A collaborative online coding environment that supports React and lets you quickly prototype and share your code. GitHub Pages plus Create React App. If you want to deploy a full React application, you can use Create React App to set up your project and then deploy it to GitHub Pages for free.
Okay. More than going to a single website and uploading this text file. So we'll just go along with what he tells me and just believe it.
And here we can see an interview
Don't
feedback
like it.
form, but it's not so great looking, some
Don't like
sort
it
of
one bit.
little weird formatting. So hopefully 0.1 is capable of improving on this. Now we'll repeat the process with 0.1. Our hope here is that using the same prompt, we'll get superior results. So I'll kick this off to generate our code.
It's very quick.
Now that that's generated, we'll print it out to have a look at it. You can see that we've got some JSX here, and I'm going to copy that into the app and print the image so that we can have a look at the quality of what it produced. And we can see here you'd have to say a superior app. So it's gone with some drop downs for the different rating numbers. It's listened to all of our instructions instead of including just a subset of categories. And it's given us a nice green feedback box as well. So a quick view of where 0.1 can help you when you have a high-level design for an app and you want a starting point. Often 0.1 will get you a bit further forward than 4.0 will with equivalent prompting. This is a static example that I've generated, but if you want to delve into this yourself and do some prompt engineering and then render your own app, then please follow the instructions in the notebook. If you want to try out the code, you can go to the link in the notebook. Cut and paste the code into the editor. And it'll render the form.
I found the thing I was
You can
looking
see the
for.
recommendation changing as
It was hands-on all along, okay? It was actually hands-on all along. I feel like there's a lot of times in this where we're given information a little bit out of order. I don't know where the end of it is. Export. I want to export. Okay, that's cool. Given the information a little bit out of order. He's saying things. I want to look down and find something. I want to go Google. I want to figure out. I want to use GPT to teach me what to do. But it had the answer all along right here. Okay. Cool.
as we fill things in.
Download a zip file that contains the React app. Oops.
And you can submit some feedback. If you're an expert in JavaScript and React, also in the notebook is a description of how to download a zip file containing an application you can run on your local computer. Next, we'll move on to editing some existing code and show how O1 can give useful feedback that will result in, again, superior code to that produced by 4.0. To compare the editing capabilities of 4.0 versus O1, we've produced some code that has some clear issues, like multiple nested loops, a lack of error handling, and overall is not super readable. What we'll do is we'll feed this code to both models, and we'll see how they clean it up. Then we'll employ a O1 LLM as a judge to rate the two resulting code blocks and tell us which one performed better.
It's not fair. You can't use O1 to judge O1. Okay.
We'll begin again with a simple and direct prompt and use 4.0 for our first generation. So the prompt, I have some code that I'd like you to clean up and improve. Return only the updated code that fixes the issues. And then we're
Okay, so this is the code. Just trying to follow for myself. I was a little distracted. This is the prompt. Gotcha. Oh, and he prints
passing
immediately.
in that code snippet, which we showed above. We'll generate this, have a look at the results. You've now generated some code, and outwardly, I mean, on first glance, it looks a little better, but let's generate the O1 code, and then we'll compare the two with LLM as a judge. Here we're going to generate the same output, but this time using O1. And again, the results look plausible here, but the best way to figure this out is to employ an LLM to compare the two. So let's do that. We're going to employ O1 as our grader here, because this is the sort of nuanced multi-step process where O1 does generally tend to perform better than 4.0. So again, we feel pretty good using it.
I wonder what the, I don't know what the ellipse is. Is it just an irregular ellipse? Looks like it's in, yeah, it's in a string.
Here. And in this case, we used, again, a simple and direct prompt. So which code is better and why? Option 1, the 4.0 code, and option 2, the O1 code. So we'll run that, and you'll see the results. The results are in, and O1's deduced that both of them are trying to do the same thing, but there are several key differences between the two implementations that make option 2 better. It's called out the readability and structure, the error handling and robustness, where option 2 has selected a more effective way of doing that, and also the data processing and calculations, the debugging and logging, and just general performance considerations. So again, a useful example of where even if you didn't rely on 4.0 for a code editor or kind of a co-pilot to help you work through issues and edit your existing code, this is an area that 0.1 does fairly well at. Great, so you should now be confident using 0.1 to assist you in coding, whether it's creating net new applications or helping improve your existing code. This is an area we're seeing a ton of uptake of 0.1, especially in the first category, where you have a high-level design and you want a really good first stab. Looking forward to being with you for the next stage, where we use 0.1 to reason on top of images.
Reasoning with
Image understanding with
images.
GPT-4o can perform well, but often needs chain of thought prompting, few shot examples, or fine tuning to achieve the best results. Conversely, 0.1 performs well at understanding images out of the box. This is due to the test and learn approach it follows in its reasoning, which gives it multiple chances to detect hallucinations before providing an answer. One use case that is emerging is to incur the latency and cost hit for 0.1 upfront, pre-processing the image and indexing it with rich details so that it can be used for Q&A later. Let's have some fun. For this image reasoning task, we're going to use an org structure of a fictional organization. This is the kind of nuanced diagram with spatial reasoning that 4.0 would typically hallucinate at, but we're finding that 0.1 performs much better, and it's because of that testing and learning approach that we referred to earlier. It will come up with a first impression of what the diagram is telling it and iterate until it thinks it has a decent outline of what the purpose is. So we're going to start off fairly basic and just ask 0.1 to tell us what this is. And then we're going to move on to a use case which we're finding customers using practically in the real world pretty often, which is that you use 0.1 to do image understanding and extract a detailed JSON that describes that image and what's going on in it in a lot of detail. And then you can do text-only follow-ups to then interpret the information. So you're not paying the extra cost and latency of processing the image every time. You effectively pre-process it with 0.1 in a very high-quality, detailed manner, and then use it for follow-up Q&A. So let's head on and see how this works practically.
Let's go. Let's go.
As always, we'll begin with our imports, bringing in our libraries and any variables that we need to import. See here are our same standard libraries. We've stored our vision request in a utils file, which we'll import here. And for this, we're going to use the new mainline 0.1 model because that one is capable of image reasoning. To get an understanding of the image that we're going to process, you should open up the org chart file, which we provided.
Wait, what is this? Why is this commented out? I don't understand. To boost our very slightly from the end of the video. Okay. Okay.
Is that one and image reasoning. To get an understanding of the image that we're going to process, you should open up the org chart file, which we provided. And you'll be able to see here that we have a CEO at the top, we have their C-suite, their managers, and then the reports of those managers. You'll begin with the simple question of what is this? So we can get a detailed rundown of what's contained in that org chart image. So we'll kick that off and display the contents. The model's given you a detailed rundown, so it's an organizational structure chart. It's called out the different levels of hierarchy and also given us a brief description of how the chart's organized and what the...
So we're using the actual 0.1 model, not the mini, and it's taking some time. How about that? Mini's really quick, 0.1's not. Oh wait, no, that was actually already finished. I just didn't click to display. It's very fast. Take it back. Why isn't my output not structured in the same or similar way? He just says, what is this? Organization chart. Huh. Yeah, I wonder why that one is very structured. Mine is not.
It's given you a detailed rundown. So it's an organizational structure chart. It's called out the different levels of hierarchy and also given us a brief description of how the chart's organized and what the purpose is. This is informative, but not super useful. So what we'll do next
Taking
is
one more.
process this into data that we can then use for follow-up questions so that we can create analysis on top of this org chart and understand the details of how these different roles hang together. What we're about to work through here is where we start to really see the improvement.
Now I want to wait for it to actually finish running. It's taking a while. Now it's taking a long time. Okay, I take back the take back. Here we go.
From 4.0 to 0.1 in terms of the quality of image understanding that we can achieve. What we saw previously with 4.0 is that it could generally give a high-level description of what was in an image, but once you start to ask nuanced questions about like spatial reasoning, like what does that arrow point to, or who reports to who in that org chart, 4.0 would give inconsistent performance and would typically need like few shot examples or fine tuning to achieve a decent level of performance. What we should see here with 0.1 is that out of the box, it will perform pretty well and be able to reduce our reasonably complex org chart to a simple JSON array, which we can then use for analysis. So to accomplish that, we've got a structured prompt here, again, using the principles that we learned in lesson 2. We have some instructions where we have a consulting assistant who processes org data, and we'd like it to extract the org hierarchy. We've given it a specification for the JSON that we want. So we want it to make up an arbitrary ID for every person, their name, their role, and then give us an array of IDs they report to, an array of IDs that report to them. So once we have this, we have something which codifies the relationships in that image as data and enables it for ongoing processing. So you'll run this and receive the results. You'll execute the cell and we print out the prompt. So there it is detailed here. Now you can feed that prompt into a 0.1 request with the image. And if we run that and print the results, we should receive an array of JSON dictionaries, which describe the different people in that org chart and how they relate to each other.
Very fast.
You can see in front of you the data representation of that org chart now. So we've got our array of dictionaries. Each one contains that arbitrary ID. And if we just reconcile the first one, we've got Juliana Silva, CEO ID 1, and we can see that she reports to no one. She's the CEO, that's correct. And her reports are numbers 2, 3, and 4. If we check 2, 3, and 4, those are indeed the CFO, the CTO, the COO. Great. So now that you've reduced this org chart to data, you can now use it for analysis. So let's step on and do some Q&A on top of this data and see if 0.1 is able to use the data that is processed to accurately answer some questions about the org chart. You can start by loading the 0.1 response as JSON, and then we can create a prompt and
So you clean the JSON by removing the... Oh, we're just removing the beginning. Wait, no, what are we removing? Cleansed JSON equals the response. And then we replace JSON. So I do remember in the past, what do you call this section? Lecture? I don't know. The past lecture, it had in the beginning triple backticks and then like Python or triple backticks and then JSX. So I'm guessing it starts with the triple backtick, the word JSON to denote the file type, and then it ends with the triple backtick at the end. So that's going to be removed. Both of those are going to be removed and replaced with an empty string. I think that's the idea there, to clean it. But then the cleansed JSON, where is that being used?
Add this data to it, and then ask some questions. In this case, you've created an analysis prompt. You're an org chart expert assistant. Your role is to answer any org chart questions with your org data. And then there's an org data XML tag here where we're going to interpolate the org data. Before you ask your analysis questions of the org data, you'll need to initiate a fresh OpenAI client. The reason we're not using the O1 vision request is that we're simply heading out with a text-only request. Now that we've pre-processed that image, we don't need to send the image every time. We're just going to use that data that we extracted and use that for our Q&A. Here you have a simple O1 request. You've got that analysis prompt that you had at the beginning, and then a structured question here. And there are two questions contained within it. So who has the highest ranking reports, and which manager has the most reports? If you execute that, you'll see the results. You can display the results as marked down here, and we can interpret the answers that we got.
So again, his answers are more structured, way more structured than mine, but we get the highest ranking direct reports. Yep, and then among the managers, Sahaya Devi. I don't know how to say that. Chahaya Devi. Sahaya Devi. Both have the most direct reports, which they both have 3 direct reports. Here. Aaron Leob.
So first of all, Juliana Silva, the CEO, has the highest ranking direct reports. That is correct. All of her reports are C-level executives. Which manager has the most reports? So first of all, it's successfully filtered for only the folks with role manager. And indeed, these two do have the most direct reports. So that is a correct answer to the question. And
I wanted to hear their names. He didn't give us the satisfaction of correctly pronouncing their names. I'm still not understanding where this cleansed JSON goes. We get O1 choices, message, content. We're replacing it to make the cleansed JSON. And then we have a JSON loader, which just loads the JSON. I don't know. Also, is this a print function? Why is it printing? Don't understand a lot
a
here.
conclusion to our image understanding task. Before we close off, I want to share one more example so that you can take what you've learned and test it out on a fresh image and domain. In the folder, you can see a photo that we've included of an entity relationship diagram. This is a great use case for image understanding. Imagine all the data warehouses that you've dealt with a complex ERD that you needed one of the local data scientists or owners of the warehouse to talk you through. Now we can provide it to O1 with image understanding.
Bro thinks I'm a coder. It thinks I've dealt with data warehouses. Come on, man. That is not what I do, my friend. All right, let's go back. He's just assuming. It's a good assumption, I guess. Most people, I'm assuming that he's correct with his assumption that most people who are watching this video have dealt with data centers or something. Never have I.
ERD
Ever.
that you needed one of the local data scientists or warehouse or owners of the warehouse to talk you through. Now we can provide it to O1 with image understanding and get it to parse it for you. So the challenge for you is to think of a few use cases for this entity relationship diagram. For example, you may want to ask O1 with Vision to generate a table of order records, which have IDs that link to these product and client tables, and then get it to generate SQL to actually query the three. Generation of synthetic data is a great use case that we've used Vision for in these sorts of cases on customer side. We're very interested to see what use.
So I think I loaded the image here into image file path, which should override this, which means that image file path, it should load this image file path in. Now, O1 vision model should be reading this ER, which it is, and it did tell me what it was. And now I can ask it questions. Oh, no, I need to extract the information. You are a consulting assistant who processes org data. Processes ERD data. Extract the information from the image you provided in a structured format. The structure should be returned in JSON containing. I don't know what it needs to contain, so it just needs to be in JSON. Just gonna drop all that. Okay. What's the prompt? So we're gonna see if we get product ID, name, price, whatever. It looks like some type of function, but I don't really actually know how these things are related in this form. So we got entities, yep, name, blah, blah, blah. But we're what are we missing? Name, product, attributes. Okay, client has CID, address, blah, 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 in the relationship. Okay. I forgot there's a name of this graph. Maybe, I don't know. Relationship, order, connected entities, product, and client. All right, that has all the information I need it. Now, I don't think I need to cleanse the JSON. Maybe I do. I'm just gonna run this without it. I'm gonna run it without the cleansing JSON because I really don't think that hat shows up anywhere. You are a URD chart expert assistant. Your role is to answer any questions with your URD data. I've already got that opened. Then I go on the question. How are I don't even know what type of question to ask about this. I guess the order has the product and the client information. I don't know. I'm just asking questions here. I ask the question, we'll see what it gets. From the ERD, the CID is the primary identifier for the client entity, and the name is the attribute to the product entity. They belong to different entities, so there's no direct link to them. Makes sense. They're only related indirectly via the order relationship, which connects a client to a product, which has a name. So the client identified by the CID and a product which has a name. That's perfect. Perfectly well. Yeah, that worked really well. Was that? He just asked me to do this, right? He asked me to figure out how to. What did he ask me? Why did I start doing this?
Use case generation of synthetic data is use cases. For now, we can provide it to O1
He wanted me to find a use
with
case
image.
of it. Use case, extract the data into text, and then use text. Use the JSON to ask questions. Also, no need to clean the JSON because that's not relevant, apparently. It doesn't show up anywhere. Notice that this did not change anything. I didn't use it.
Understanding and get it to parse it for you. So the challenge for you is to think of a few use cases for this entity relationship diagram. For example, you may want to ask O1 with Vision to generate a table of order records which have IDs that link to these product and client tables, and then get it to generate SQL to actually query the three.
Oh.
Generation of synthetic data is a great use case that we've used Vision for in these sorts of cases on customer side. We're very interested to see what use cases you come up with, and very excited to see what you use O1 with image understanding for. Look for.
That makes even more sense to create synthetic data. I have no idea how to do that. I don't know enough about. I don't even know what kind of coding we're doing right now. We're doing Python. I don't know enough about Python coding to create SQL synthetic data, but yeah, it makes sense. It's pretty cool.
Forward to catching up with you on the next one,
Yeah.
where we'll be going into meta prompting, how to use O1 to automatically optimize your prompts. Look forward to seeing you there. Optimizing to production level accuracy is one of the biggest pain points we've seen developers experience when working with LLMs. With so much guidance for prompt engineering, RAG, and fine tuning out there, figuring out which optimization you need to hill climb on your evals can be a difficult problem to frame and solve. Luckily, it appears to be one of the use cases that O1 is very capable of. In this session, we'll focus on how to use O1 Mini to work with a set of evals to optimize our prompt for a task and improve on our eval scores. Let's dive in.
Welcome to your final lesson on meta prompting,
Okay.
the practice of using an intelligent model like O1 to iteratively improve the instructions of a less intelligent model. The use case we're going to focus on here is routine generation. This is a common use case where existing knowledge base articles are written for human consumption and are difficult for LLMs to follow reliably. We're going to use O1 to read in these knowledge base articles and convert them into a routine, which is optimized for LLM usage. We're then going to feed that routine to a 4.0 model, which will try and pass an eval with that routine. We're going to
Some language here I don't understand. The language being routine. I don't know what a routine is, or why re-evaluating a routine. Optimizing to production is one of the biggest pain points we've seen developers experience when working with LLMs. With so much guidance for prompt engineering, RAG, fine-tuning out there, figuring out which optimization you need to hill climb on your evals can be a difficult problem to frame and solve. Luckily, it appears to be one of the use cases for O1 that O1 is capable of. In the session, we'll focus on how to use O1 Mini to work with a set of evals to optimize our prompt for the task and improve scores on our evals. The task and improve score. Okay. So there's some sort of test for some reason. We're having a test of 4.0 to do something, and O1 is going to make the prompts better.
To do this a number of times, and after every iteration, we're going to hand the eval results and the routine we used back to O1, which is going to try and improve the routine to solve the issues that it saw in the eval.
Gotcha.
This iterative process is known as metaprompting, where we use a more intelligent model to improve the instructions or guidance for a less intelligent model, and then use the eval results to iteratively improve them. There's a few steps there. So before jumping in, I want to summarize. Step 1, we're going to take on a flight cancellation and changes policy as our example here. Our step 1 is going to generate a 4.0 routine. We're going to read in a policy that was written for human consumption, and we're going to give that to O1 to generate a routine to implement that policy, which contains a prompt and also a set of tools which we've given to O1 to let it know that it can use some external actions to carry out the policy. Step 2 is to evaluate 4.0's performance at carrying out that policy on an eval set. That will let us know how well our conversion process has worked. Step 3, the critical step, is where we'll perform the metaprompting, where we'll then do a series of iterations where 4.0 will try and carry out the routine, and the resulting eval will be given to O1, which will then try and improve the routine and give it back to 4.0. We'll try this 3 times, and hopefully one of these iterations will end up being a superior routine, which we can then adopt and take into production. Let's begin with step 1. You'll begin, as always, with your imports. We'll ignore warnings. We'll also load up our OpenAI API key and import our libraries. We'll also bring in a GPT model and O1 model, which we've defined in a config file. Feel free to change these if you'd like to try more intelligent models, but in this case, we're going to use GPT 4.0 Mini for our GPT model, and for our O1 model, we're going to use the mainline O1 model so that we can take advantage of its ability to use structured outputs and tool calling. We're also going to import a function that will compare 2 different string inputs and show the differences. So this will come in handy as we go through the metaprompting loop, because we may want to review O1's work as it reviews routines and updates them. What you may...
I've never seen this before. I didn't know you can do this so easily. Compare strings. Oh, it's a defined function. I gotcha. Create red lines, compare strings, diff. No, it's pretty simple. I didn't know that's such an easy thing to do. Red line, or is, yeah, red lines here. It's a library. Gotcha. It's a whole library. Maybe it's not that simple. Compare strings. Okay.
Find during this metaprompting is that O1 may overfit to the eval results that it sees. And to check that it's not doing that, we want to do some visual checking of the resulting routines that are coming out of the metaprompting process. You're now ready to begin with step 1, where we'll generate a routine from our original human written policy. We'll begin by printing the policy. You can see here the purpose, a few notes on the tone that the agent should use when they're using this, and then a set of table of contents here. The main thing to take away is that nowhere does it explain to the LLM where actions are external and where it can fully take action with the contents of this policy. As well, all the details are spread throughout this document, and the model will have to jump up and down the document to answer questions using a lot of logic as it works it out. We're going to rewrite this with O1 so that it will be much simpler for the model to follow these instructions reliably. Here's a prompt for O1 to carry out this conversion process. This conversion prompt has an objective at the top where we tell the model again what its purpose is, and then some instructions on how to carry out the process. You can see here that we are using the advice from earlier lectures, setting out a structured format that it should use, and also specifying items like it should only use the available set of functions. And we're importing a list of tools from a config file, which are the external actions that the model will be able to use to carry out this policy. We're then going to ask it to convert the following policy into a formatted routine, ensuring that it's easy to follow and execute programmatically. And we're reminding it to only use the functions provided and not to create net new functions. This is something to think about because in real life, we've seen customers use this approach, and sometimes you do actually want the model to suggest new functions, which you might need to create and then add to your list of function calls for the eventual LLM agent to carry out. But in this case, we're going to restrict it to the available functions.
Interesting. Ask it to create new functions.
I'll save that prompt, and we'll move on to create a function. Carry this out. This is the generate routine function, simple function that takes a single argument, the policy, and uses that conversion prompt. In this case, we're going to use O1 mini to give us our baseline quickly. Save that function, and we're ready to generate our routine, which I will do with this command. Congratulations, you have your first LLM generated routine. Let's run this command to take a look at it. You'll see here, the model has followed our instructions. It has broken out the various processes that took place within that policy into distinct demarcated sets of instructions, and it specified what function the LLM should call to execute each one in order. This will make it simpler for the model to go through the logic or the if-then-else of carrying out each of these instructions contained within the routine.
So this is again this is a very similar to what we discussed earlier about this categorizing and sorting. You've got a scattered list of instructions. O1 can categorize them and sort them into a very easy step-by-step logical list, which I like. I have not used any of the reasoning models to do that, but I think that would be very helpful for me. I guess I've loosely done it, but I've never explicitly done it. So I like this, and I want to use it.
The last step before we evaluate this is to check that there are no data quality issues with the routine that our LLM has generated. I'm going to bring in a function here that will let us check for overlap between the functions that we defined at the start and the routine that's being generated.
Okay.
This function will perform some regex between two lists to find out which items exist in one and not the other. And this is what we're looking.
What is regex?
Regex, short for regular expression, is a powerful tool used for matching patterns within strings. It allows you to define a search pattern using a combination of literal characters and special symbols. These patterns can be used for searching, extracting, and manipulating text. For example, you can use regex to find all email addresses in a document, validate formats like phone numbers or dates, or replace specific patterns within text. Regex is supported in many programming languages and tools, making it a versatile and essential skill for text processing.
So I'm using the regex. Oh, function names. So, 1 second. I'm a little confused about something, so give me a second.
Take your time. If you have any specific questions or need clarification on how to use regex for function names or anything else, just let me know.
So I've got a variable that's called patterns, and it is equal to r r quote backtick uh, uh, parentheses period star question parentheses backtick quote. That I don't know what that means.
Got it. That pattern is a regular expression designed to match function names in some programming languages, like Python. Let me break it down for you. R:, this indicates a raw string in Python, which means backslashes are treated as literal characters and not as escape characters. This is the core of the regex. It matches a pair of backticks enclosing a function name. This pattern is technically a capturing group containing a section, which means whatever matches inside the parentheses is captured for later use. This part matches any sequence of characters that are not a backtick. The X means it will match as few characters as possible, non-greedy match. The other part is that this regex pattern finds text enclosed in backticks and captures the content inside the backticks. If you're using this pattern, it likely helps identify function names or other identifiers surrounded by backticks in a string.
Are period asterisk question mark, are those wildcards or what is happening there?
Yes, those elements in the regex pattern are indeed acting like wildcards. Dot, this matches any single character except for new line characters. Plus, this is a quantifier that matches 0 or more occurrences of the preceding element. In this case, it's paired with the dot, so .mx matches any sequence of characters of any length. When used on...
Bro, you're hallucinating right now. The R makes it a raw string. Gotcha. Literal backtick character. Gotcha. Okay. Dot any character except new line. Yeah. Question is a non-greedy match. As few characters as possible while still satisfying the overall pattern. What is it? That's what non-greedy means. Okay. Star question. Okay, so 9 o'clock. Anything before, anything that isn't a new line, I still don't quite get it. Capturing group captures the text match inside of it. All right, probably not super important for me to know. So
Looking for.
we'll continue.
So there are no items in our routine that are not in our list of functions. That's great.
Items in A that are not in B. One. Items in B that are not in A. Oh, one as in there's none. Gotcha. Understood, I think. Items in B that are not in A. Here. So A is this list. B is this list. But we made functions and we're looking for functions. I really don't understand.
Great. We don't want that. And there are 3 functions in our list of function definitions which weren't used in the routine. But that could actually be okay. So we'll run the evaluation and we'll check whether these should have been included. And if so, we'll need to make some adjustments. But for now,
Yeah, because it's definitely not this list. We're looking for functions. Where are the function names? Next function text. I'm guessing this is not incredibly important, and also I'm just kind of running low on time, so I'm gonna just kind of continue past without understanding a little bit.
We've generated our routine from a human written policy. We've completed step 1. So we're ready now to move on to step 2, which is evaluation. For step 2, evaluation, I want to go through a little bit of theory of what's going on under the hood before we dive through the code examples.
Okay.
For each eval example, we've recorded a request that this customer is going to start with, and then a bunch of information that the customer can use, as well as an expected response. And that's the correct response that this customer needs to receive from our assistant if they're going to get what they want out of this process. Now, the reason we've designed our eval set like this is because of the difficulties of evaluating a multi-turn interaction like these customer service routines. To recap what's happening here, we're starting off with our O1 generated routine, which is given to 4.0 as the policy that it needs to follow. Then we begin with the customer request, which will be something hard-coded like, I would like to cancel my flight, please. Now, our 4.0 agent might need to do some verification of that customer before actually getting to the refund stage. So to enable the conversation to continue, we also spin up a 4.0 customer who uses this request and information that we've defined to continue the conversation for multiple turns until we reach a function call, at which point we'll terminate. Certain function calls we're going to ignore, like check ticket type, because those are generic function calls which the 4.0 agent will need to carry out to figure out whether, for example, the customer is eligible for refund. So a multi-turn interaction could look like this, where the customer provides their booking reference, their name, and their flight number, and the 4.0 agent goes back and forth with that customer for a couple of turns before selecting an exit tool. And we then compare that to our eval set, and that will be either true or false. We evaluate 2 things for each record. First, whether the right tool is called, and second, whether the correct arguments are provided. This is what each example in our eval set is going to look like. Again, this is a generic framework. This isn't unique to metaprompting. This is actually a useful pattern for multi-turn evaluation that's usable in any context, even if you aren't going to do metaprompting. But our hope is that in metaprompting, it will give the model that's optimizing the routine a few more options to optimize to enable the agent to perform better on subsequent iterations. So now we'll jump into the code and try this out for real. To begin the evaluation step, we need to define a few functions. The first one is the agent response function. This enables our agent to respond to the conversation which is continuing. So the inputs to this function are a transcript, which are all the user and assistant messages so far, a policy, so the routine that the agent should be following, and a model that we're going to use. We're also going to invoke the tools that we provided at the start, and we're also going to disable parallel tool calls. That is a choice for simplicity here to make this easier to run through. But in your use case, you may actually want to enable parallel tool calls and allow it to, for example, call a verification tool and the refund tool together. And externally, you can decide what order you execute those in. But to make this simpler, but at the expense of more turns, we're going to turn parallel tool calls off. I'll save that function, and we'll define a couple more functions. The next 2 are firstly a simple function to handle any null strings that we get from each record in our test rows that we're going to send through this function. And then the more important function called process row, which will be run on every step in the eval set. And every one of our eval examples will have the key attributes extracted. And we'll also stand up a customer prompt where the synthetic customer who's going to talk to our agent will be defined with any variables that we've input from the eval data. There's a few that we're going to instantiate in the system prompt so that they're present for every interaction for the customer. But for other ones, like for example, the ticket type or fare rules, our agent will have to call the right function to ensure that those are present in the conversation for our agent to respond correctly. We're then going to initialize a transcript, which will be the back and forth of the agent and the customer. And then we're going to loop through a number of iterations. We've put a breakpoint in here just in case it starts looping forever. We're basically going to fail that iteration and just finish with none for the outputs. And if we do get a response, we're then going to continue the conversation. So if we don't get tool calls, we're just going to get our synthetic customer to respond. Otherwise, we're going to make a decision based on what the tool call is. So for tools like verify identity or ask clarification or check ticket type and similar types of functions to that, we're going to continue the conversation. But for some, we're going to generate a synthetic customer message, which will let us continue. For some, we're going to synthesize a tool response, which is usually inputting some of the values for that eval row. So for example, if we call check ticket type, we're then going to interpolate the ticket type and fare rules for that customer's booking. So this is really the critical function to execute our eval tests. We're then going to wrap that in the evaluate function calls function, which will let us use a thread pool executor to process these in parallel. So I'll save that, and we're now ready to execute the evaluation. But before we do that, you should have a look at the data that we've provided.
I'm just looking at this added function here, filter messages, which is not in the video, but it is helping the transcript be smaller. Convert the item in a string, check if it is in it. Okay. It just appends only the chat messages and not some of the other stuff, I guess. I'm not really sure. But it's good to see. I'm having an issue. It's not really an issue. I'm having a concern with one of the things I'm building, that there's going to be too much. The transcript's going to be too long, or the JSON's going to be huge, and I'm going to be using it back and forth. So the fact that we're needing to filter some messages is a good idea, and I need to figure out how to do that myself. So cool.
Here's the eval dataset. The key things to pull out are that each customer has a name, a booking reference, a flight number, an expected function, and expected inputs to that function. Those are the two fields that we're going to evaluate for each of our evaluations. We've also included a few details. So for some of them, we have a refund amount. For some of them, we have fare rules, a ticket type, etc., which may be critical for the agent to extract with certain tool calls to answer the customer's request successfully. The request is the verbatim request that this customer will initialize the interaction with the agent for, and the context is generic context, which goes in the customer's system prompt to enable them to carry on multi-turn conversations with a little bit more context if they need it. These are pretty basic, but you can imagine in a real interaction where there might be a ton of supporting data that the customer may need the agent to know, that you would want to interpolate into the context to enable a multi-turn conversation to take place. So these are our eval examples. The last function we'll define before we run the evaluations is a display row function, which will display a single row with the full transcript so we can see exactly what the back and forth interactions look like in practice. With that, we're ready to run our evaluation.
Okay,
Let's kick
run
that
it.
off. You now have some baseline results. We can have a look at this data frame to see exactly how we performed. So our accuracy is 64%.
Taking me a while.
And we can, by looking across a couple of these, we can see where the model has gone wrong. So for example, for our first example, it was supposed to be a partial refund, but instead we've offered a flight credit, which is incorrect. So that has been assessed as a fail. The second one looks correct. We should have applied a change fee for booking reference DEF456, and we have. Great. I'll print a single row.
Request, content, expected function, and actual function. Process, partial refund, got it right here, got this right here. Process full refund, rebook without fee, got that one wrong. Okay. Offer flight, got it, got it, got it, got it. Didn't do anything. Okay. So that's wrong. Oh, did it loop? Probably looped at some point and just broke it. Here, right, here, wrong. Okay, okay, cool. Can see
In
the eval.
detail, so we can see how the transcript actually unfolds for one of these. This was our first failed record. You can see here that we actually had quite a few turns.
So for me, it wasn't actually The first failed one was 2. I don't know why it's displaying in this way. I don't understand that display issue that we're having there, but whatever.
And so, for example, the user said, I want to cancel my flight because of a medical emergency. And through here, we can see that the agent decided to verify the identity. And once it had verified it, it offered a full cancellation, but it asked for a medical certificate. It asked for the details. And then our model then failed to continue the conversation. We can see a failure of the customer. And
I'm gonna pause for a second. I just need to get some warm liquid in my throat. All right, that was much needed. Got some tea.
And in the end, this probably hit the 10 turn limit and spooled out. So a fail.
So here, his example is different from my example. My flight was canceled by the airline. I want a refund. I might assist you today. Are you looking to cancel or change the flight? I'd like to request a refund for my canceled flight. My booking reference is blah. My flight number is blah. Airline canceled the flight due to weather conditions. Found the booking reference. Did the ticket type refundable, fare rules, give the full refund. Tool call ID, call, okay. Tool call, refund, rebook without fee. Why'd I do that? I just made a weird error. Okay, that's interesting.
Example. Hopefully our meta prompting can fix this. So with that, we've got our baseline run. To recap, we scored a 65%. That's not great, but hopefully a lot of room for our meta prompting run to improve. Now you go through step 3, the most critical step of this process, where we improve the 4.0 routine using meta prompting. First step is to define a simple function here to get a response from the OpenAI API, chat completion. And the one nuance here is we've added a response format parameter.
No
if we
response.
do supply a response format, then we want it to use structured output. And the reason for that will become clear in a minute, but the main summary here is that the structured output schema we're going to look for is a final answer, which is going to contain a updated routine from the meta prompter. So we'll see why that's important in a second. The next step is to define our prompt. And here we have it. So we're going to insert a user message here for O1. It has instructions, first of all, where we're telling it that it's an agent responsible for improving the quality of instructions that it's presented with. We also give it the criteria, where it's meant to analyze the existing instructions, understand any issues, improve them to address the gaps, and ensure that any changes are compliant. We also repeat the instructions from above that it should only use the tools that are provided. We've also suggested that it should change the format. This is just an example. We have seen with meta prompting that sometimes, whether it's an XML or Markdown, can actually make quite a big difference for certain data sets. The thing I would consider here is what's the specific guidance that you would give O1 based on your use case? There may be particular optimizations that you suspect will be useful for your data set, and here is the place to give them.
I might want to just copy this. This seems interesting. Understand which behaviors led to the failures.
We then framed the model that has been given 4 items, which is the ground truth policy that it began with, the list of available functions, a routine instruction, which is the latest one, and then a set of results. and we may provide it with a history of edits and evaluations. So this just means that we may give it multiple previous routines and evals to show it how well they've all performed. Then we give it the data that it needs, which is first of all the original policy, which will always be static here in the available functions, and then a conclusion, which is to return the improved policy exactly as written within the defined JSON. And this is where we'll use that structured output schema. So effectively, the meta prompter will generate a new routine given all the previous iterations and these instructions, and then we will extract that using structured outputs into the format we need to input as the routine for the next iteration of meta prompting. So I'll run that and
Okay.
move on to the next step, which is to import tick token and set up tick token to get the tokens from a list of messages. This will be useful for our meta prompter again. We will try and insert as many previous examples as we can so that the model will not repeat mistakes that it did in previous runs of meta prompting, but we are limited obviously by the token limits. So this is something that we've put in to deal with that. So the next and primary step is now to execute the meta prompting. So the way we do that is, first of all, to start with these different lists. First one is a list of routines. Second is a list of results or data frames of eval results. And then the third is the accuracies, which we're going to plot at the end to figure out which of these routines we want to keep. And then we have our O1 messages, which is just the O1 message from above. Then we have our max tokens that we're going to append previous eval runs for. And then we start our meta prompting. So we're going to loop 3 times. This is just an example that we're doing to try and minimize cost. In fact, with this approach, the model is going to try all sorts of different methods. It typically will not just gradually bring itself to the correct answer. It will often try completely different things a few times and worsen the results before they get better. So it may be worthwhile to do 5, 10, 20 iterations to get this right.
Well,
What we do here is if we do have any previous eval results, then we start them here. We start to append previous eval messages if we have the tokens. If not, we just do nothing. We did leave a placeholder here to add some truncation logic. We chose not to for this course, but if you did choose to truncate them and still include them in some way, like maybe summarize them rather than include the entirety of the previous routines, then you can do that here. But in this case, we'll just ignore them if we don't have tokens for them. Then we get the updated routine from the meta prompting assistant. So we call our get OpenAI response. We use our structured output and we get a routine JSON. We then turn that into a string and then load that into a new routine and append that to our routines object. And then we're ready to repeat the exercise above, the evaluation. So we load in our data frame again, and then we get our results and our accuracy. Then we'll append those. We'll list the IDs of the failed rows. This will be useful for us just to have a sense check of the sorts of things that our model is getting wrong. And then we start building up a new O1 messages that includes the new most recent routine and then any other ones which we can fit in. So this is the logic for the meta prompting.
gotcha. And the accuracy went up. With the first one being wrong, but these are all only the wrong ones. Wait, is that right? No, no, only the first one was wrong. Oh no, these are only the wrong ones. That's correct. So the first one, 70%. Second one, 76. Third one, not shown.
So I'm going to execute this and let's see how our model does. That's the meta prompting completed. So we'll dive in and have a look at our results. Our first iteration didn't do too well with 71%, but if we scroll down, you can see the errors being logged. We can see a couple examples here. Let's just look at the 3 results first before we dive in. Oh, iteration 2 looks pretty good. 88%. That's not bad at all. So only a couple errors with that one. And then iteration 3, still pretty good, but not as good as iteration 2. So ending at 82. And if we take a look at a couple of the results, so for example, this one.
It looks like none of them, so it's just taking a while to fully populate, but they're not changing. 76.47 is the same. 7647, and then yeah, that was it. 7647. Even for iteration number 1, 7647. Nothing's changing.
The request was, I need to change my flight within the next 7 days. You can see that the model did actually get the right function. So process change no fee was the function in both cases, but the arguments didn't match. So we got a failure. And actually, this is maybe actually an issue with our eval function being a bit too strict, or maybe we haven't given enough context for the synthetic customer to actually properly supply this information. But whatever it is, still looks like pretty encouraging. So from our baseline, we've improved over 10% with a couple runs of metaprompting. So pretty good. Just to chart those out, I'm just going to make a quick plot here. And here we have that plot. So our baseline was just over 70%. It's consistent for the first metaprompting run. Then we got all the way up to 88% and then down to 82%. So this is the run that we'll go with as our best routine. Got a bit of code here to just print that so we can get an idea of what that routine looks like. And here it is. Looks like the model figured out a slightly different way of annotating the different sub-bullets. And for whatever reason, this seemed to work pretty well. So fairly interesting. And this is an example of some of the less traditional ways that the model will approach metaprompting. And in this case, it's got a positive performance boost. So potentially we can use this as our golden routine going forward and do further iterations either manually or with more targeted metaprompting to see how much performance we can squeeze out of this one. So that is the completion of our metaprompting lesson. To recap what we did, we started off with a policy that was written for a knowledge base for human agents to use to answer customers' questions. We used O1 to convert that into a routine that was optimized for LLM consumption. Then we created an evaluation where we could run multi-turn evaluations, where an AI customer would take a request and then play off against our AI agent that we'd built using our routine to answer questions. And we weren't entirely happy with those results. So we then did 3 rounds of metaprompting, which was the third step, where we got O1 to look at each set of eval results and iterate 3 times to try and get the best possible routine. And in doing so, we got a boost from our baseline of about 70% all the way up to 88% accuracy on our eval. We hope this lesson on metaprompting has been both informative and also served to stimulate ideas of where it could fit in your workflows. Where could you use this? We've used this for customer service here, but really anywhere where we have these multi-turn conversations, we want to iterate over a number of variables, we maybe have a bunch of tools that we want to iterate through. There's a huge number of applications for this approach. We're extremely excited to see how all of you use these capabilities and hope that you've enjoyed the course as a whole. Look forward to seeing what you build and forward to the next one.
Great. Yeah, I guess the instructor also did this all in one day because his voice was kind of going out at the end there. I think it was too much for me to do all together. Though I think I learned everything. There were some parts I just didn't understand a little bit towards the end. Some parts were breaking, obviously, with the evaluation. It broke a bit. I guess I didn't explain it, but the function just broke and rate limited. But however, I did learn a lot, and I think this is all immediately applicable to me today. This very hour, I will be using some things that I've learned in this course. So helpful for me. But I think I probably should have taken a break at some point.
Of course, you learned about how our reasoning models work, how to prompt them, and some great use cases that developers are delivering in the real world.
Mm-hmm.
You now have what you need to start building with this new class of model. We are very excited to see what you come up with.
Well, thanks, guy. Don't remember his name.
Welcome to Reasoning
Colin.
with O1.
Thanks, Colin. Colin and Andrew. I can download the Jupyter notebooks. Take regular breaks. See, I didn't do that one. Oopsies. Practice active learning. Don't just read the notebook, run the notebooks. I did run the notebooks. Engage with the community. Where's the community at? Hey, yo, community, where you at? Chat, is this real? There's no community here. They're in my walls. Enroll other short courses. Okay, that was everything. Well, yep. Feedback, any comments? I liked it. Approval. No, I liked it. Just no problems. Feedback on the platform, user interface, functionality. Let's go. I don't remember where there was at one point where the cleaning the JSON was not relevant. Functionality was good. Just all right. Would I recommend this? I already submitted. I don't know, because I'm literally recording this right now and I'm going to post it. Is that a recommendation? I think it is. I think it is. I'm extremely likely to do this because I'm actually doing it right now. All right, that has been this course. We have all together learned about meta prompting and about visual reasoning and about using reasoning models to guide, to instruct the non-reasoning models, and the fact that you cannot or should not use chain of thought, and the fact that we should use reasoning models to create code and check code. There's a lot there that I actually learned and I can use today. So I just wanted to go through that course and I figured I'll record myself. So that's what I did. And that's the end of this.